It's day 13 of the advent of compiler optimization, and today we're going to continue the theme of loops and look at some of the other things that the compiler can do to make loops go fast. We're back to looking at the sum routine that took the vector. One of the first things we looked at in this series, and hiding in plain sight is an optimization that we kind of brushed over. If you remember, we looked at how the vector stores both a sort of begin and end, and we're calling vec.size in the loop here. So in each iteration, we're saying set the index to 0 at the beginning. For each iteration, if index is less than the vector of size, then we're going to continue. And at the end of each iteration, we're going to increment the index. Now, this call inside, this vec.size, we might reasonably expect the compiler to call vec.size each time within the loop because that's what we're asking it to do. However, the compiler is smart and it's realized that that size can't change as a result of anything that happens in the loop body. And as a result, it has done it ahead of time. So you can see that on the right-hand side here, this shift arithmetic right and the subtraction is all part of getting the size, where we get the end minus the begin and divide by the size of an integer. It's as if we'd done something like const auto vec underscore size equals vec.size outside of the loop, and then wrote vec underscore size in the loop here. Now, back in the day when I first started writing C and C++, compilers weren't necessarily as smart as they are today. And so I got kind of used to pulling things manually outside of loops that didn't have any effect on the body or didn't change as a result of the body. But nowadays we can pretty much rely on the compiler to do most of these things for us. There are some interesting side effects though. The compiler has to be able to prove that nothing can possibly modify any variable that it has decided to rely upon in either an inline function like the size call here or anything else that it is hoisted outside of the loop. So if I undo back to vec.size, so this is what we had written before. Let's say we wanted to count how many times we had how many individual elements we'd summed. So let's put a horrible global variable of std size t, num counts or num adds equals 0. And we're going to ignore threads here. Seems reasonable. And we're just going to say plus num adds. So we're just counting how many times we're doing adds. Now that's a terrible thing to do. You'd probably do something else outside the loop, but look how much it has changed our loop body on the right hand side. As you might imagine, we are reading out the number of adds into an RDI register here. We're doing the work of the loop body here, and at the very end it's adding to RCX, which is the loop counter, how many times it went round. It's adding the old value of num adds, and then finally it stores it out here. So it's done some clever things here. It's realized that it doesn't have to increment num adds inside the loop every time. It can increment it once at the end and write that out to the global variable. But look what happens when I change the type of num add. So at the moment it says size t, which is a sensible thing to be. But if we were to, for example, to pick an int here, now look what's happened. So we're still reading it outside the loop, we're doing our shifts, and then inside the loop body now, we're actually writing out to num adds every single iteration. We've lost this trick where it was only deferring it to the end. So we're spending a bit more time in the middle of our presumably expensive loop iteration. Why is this? This all comes down to some of the rules of C++'s aliasing. The compiler is not allowed to assume in general that a pointer to an object is the only pointer to that object. And as you know, hiding away inside that vector that we're passing in are some pointers to integers. There's a pointer to the begin, there's a pointer to the one past the end, and then there's the pointer to the end of the storage, but the ones we care about are the begin. Because it's an integer pointer, the compiler can't assume that any other integer of unknown provenance, it doesn't know whether or not that integer overlaps with the integers that the pointer is pointing at. And so every time we increment num adds, for all the compiler knows, the pointer that it's walking inside here, inside the vector, might actually overlap with it. In which case it has to write to the variable every single time because it would change the result. Now, you and I can reason and say that we know that inside a vector, those pointers always point at the heap, and that heap could never overlap with the num_adds global variable that we've got here. So we could prove to ourselves that, but the compiler can't. That's beyond the reasoning capabilities of the compiler or the expectations we have of it. So just be aware of this. We'll be talking a little bit more about these kinds of issues later in the series. But for now, just be aware that certain things can be proven to be constant and are moved outside of the loop. This is called loop invariant code motion, but things like aliasing might prevent it from happening. Less of an optimization today, I suppose, other than explaining something that we'd already seen was an optimization, and that sometimes that optimization can't be applied for non-obvious reasons. Either way, I look forward to seeing you tomorrow.